So today we'll be looking at chemical equilibrium. Okay, equilibrium is one of those topics that are easygoing and straightforward. There's nothing there. Now, before we look at equilibrium, let us consider a reaction. Okay, look at this reaction: water in the liquid state turning into water in the gaseous state. Now, this is simply just evaporation of water from the liquid state to the what? To turning into steam, right? Now, this reaction, if it is reversible means that a reaction that can go forward and also come backward. If this reaction is irreversible, it means that the reaction is taking place in an open system, because it's only when the system is open that the reacting material will go and never to return. But if the reaction is happening in a closed or isolated system, then what happens is that the reaction will go forward and still comes backward. Okay, so it means that the key word I want to let you know is that equilibrium takes place in a closed or isolated system where none of the reacting vessels are allowed to escape. Okay, none of the reacting materials are allowed to leave, because once anyone leaves, then the reaction cannot turn back again. So equilibrium takes place in a closed system, okay, or isolated system, and the reaction in equilibrium is a reversible reaction, indicating what? The forward reaction and the backward reaction. Now, when does equilibrium take place? Equilibrium happens when there is no net observable change taking place between these two rates of reactions. Okay, when the R1 is equal to the R2, when this R1 equals R2, then equilibrium is said to what? Occur. Now, this equilibrium is very, very important because we can use it in industries for so many things. Okay, but before we go into equilibrium, let's look at what we call the law of mass action. Okay, the law of mass action. The law of mass action. The law of mass action. Law of mass action. The law of mass action states that the rate of a reaction is directly proportional to the active masses. Okay, active masses. Okay, this law was proposed by two scientists called Goodberg and Wedge. Okay, so this law is saying that the rate of a reaction R is directly proportional to the active masses. Okay, but we can restate this law by saying that the rate of a reaction is directly proportional to the concentration of the reactants. Okay, we can say that the reaction is saying that the rate of reaction is directly proportional to the concentration of the reactants raised to their what? Coefficient. Raised to their coefficient. So it is from this law of mass action that we were able to derive the equilibrium constant expression. Okay, so how do we derive the equilibrium constant? I'm not going to derive it, I'll just write the equations for you. Now let's consider we have a reaction A plus B to give us C plus D. And let's assume that after balancing this equation, we have A, we have small b here, we have P, and we have Q. That is the coefficients from a balanced chemical equation. Okay, now if we are to write the equilibrium constant of this reaction, equilibrium constant K, equilibrium constant is K. If you see me write KEQ, it means equilibrium constant. Equilibrium constant K is equal to concentration of C, or the value of C raised to the power multiplied by that of D raised to the power of what? Q, all over that of A raised to the power of small a multiplied by that of B to the power of what? Small b. So it's simply, you can say that equilibrium constant is trying to say what? The concentration of the product to the power or to the coefficient, okay, all over that of the what? Reactant raised to the power of what? The coefficient. Okay, the coefficient is the values you get from the balanced chemical equation. So this equilibrium constant is of three types. We have equilibrium constant. The equilibrium constant can be expressed in three ways. It can be expressed in Kc. This is the equilibrium constant for concentration. It can be expressed in Kp. This is the equilibrium constant for partial pressure. It can be expressed in Ka, equilibrium constants of activity series. Okay? Now, these equilibrium constants can be expressed in three different ways, and we can also write their expression in three different ways. Okay? For example, if you are told to write the equilibrium constant in terms of Kc, this here satisfies this. But in terms of pressure, Kp will be equal to the partial pressure of this C, all of to the what? Of the C raised to the power of what? P, multiplied by the partial pressure of D to the power of what? Small q, all over the partial pressure of A to the power of what? Small a, multiplied by the partial pressure of what? B to the power of what? Small b. So this is how we write it in terms of what? Kp. In terms of activity series, you just replace this P with what? Capital with A. Okay? Replace this P, all the P's here, with A if you want to write in terms of what? Ka. So we are going to look at a simple example on how we can write this equilibrium constant. Now, how can we write this equilibrium constant? Okay? Now, let's assume that we have this reaction, nitrogen plus hydrogen, to give us ammonia. Okay? Remember, this is a gas, this is a gas, this is a gas. But before I write this equilibrium constant, I want to use this concept to explain homogeneous equation. How can you know if a reaction or equation is homogeneous or heterogeneous? Now, homogeneous equation means that all the reacting materials are in the same phase. What's the same phase? This one means same phase. What does same phase mean? Same phase means they are in the same state of matter. Gas, gas, gas. Okay? But when we have a reaction in which there is a mixture, okay? There's a mixture of both gas, solid, and liquid. Mixture. That one is called, so different state. So this one is called different phase. Different phase. So the difference between a homogeneous and a heterogeneous equilibrium or equation lies in the what? In the state of matter. So if this one was, let's say, in solid state now, then this equation is not going to be a homogeneous equation. Instead, the equation will be what? A heterogeneous equation. But this guy is in what? Gaseous state. So this equation is called a homogeneous equation. So when we get to catalysis, when we look at catalysis, we also have homogeneous catalysis and heterogeneous catalysis. For catalysis, you will now be talking about the catalyst, okay? If the catalyst and all these guys are in the same phase, if the catalyst and all these things are in the same phase, then we'll call that a homogeneous catalysis, okay? Catalysis. But if the catalyst or anything here is different in different phase, gas, solid or liquid gas mixture, then that kind of catalysis is called a heterogeneous what? Catalysis. So I'm not talking about catalysis for now. I'm talking about equation, homogeneous equation and a heterogeneous equation. So you should be able to differentiate between a homogeneous equation and a heterogeneous equation. Now, my concern is, how do we now write the equilibrium constant of this expression? How do we write the equilibrium constant of this expression? Okay? How do we write the equilibrium constant of this expression? Now, in terms of Kc, if I want to write the equilibrium constant in terms of Kc, it's simply going to be Kc is equal to, but before you write the equilibrium constant, you must make sure that your equation is balanced. A balanced equation obeys the law of conservation of what? Mass. Mass is not destroyed. It's converted from one form to another. So balancing this equation, I'll put 2 here, I'll put 3 here. I think it's balanced now, right? So now, equilibrium constant. Equilibrium constant of solid and liquid is equal to 1. Equilibrium constant of solid and liquid is equal to 1. Okay? So with that respect, I will check if any of these guys are in solid or liquid state. None are in solid or liquid, so we can write the equilibrium constant in terms of concentration, Kc. So in terms of Kc, is going to be bracket open. From the product, you have ammonia, NH3. What is the coefficient of ammonia? 2. Raised to the power of 2, okay? All over concentration of nitrogen multiplied by that of what? Hydrogen to the power of what? 3. That's how we write the equilibrium constant in terms of Kc. Okay, in terms of Kp, you can write the Kp using P, okay? this bracket will now use P to replace it, and then ammonia to the power of 2. The same thing happens to this one. So these are the several ways you can write or express equilibrium constant expression. Okay, so I have done the law of mass action. You should know what the law is trying to say. From the law of mass action, that is how we got the equilibrium constant. Okay, and there are 3 types of equilibrium. We have the Kc, the Kp, and the Ka. So then we are going to look at the properties of equilibrium constant.